Streamlit is all about building data applications. Let's get some data so we can build a proper application. Welcome to this video on Streamlit. My name is Kevin Fiesel, and I'm the proprietor of Catalaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. In the prior video, I gave you a bit of a primer on Streamlit, explaining where it fits in this world of code-first platforms for displaying data. In this video, we will pick up where we left off and introduce some data into the mix. There are a few items I want to cover today, but instead of going to a classroom, I'm going to change it all up and take us straight into the demo, so see you there. Welcome back to Visual Studio Code. In the prior video, I created this rather small Streamlit application. I'm going to pick back up where we left off. First up, let's make sure that I am in the correct virtual environment. In Windows, I can do so in the command prompt by running demo app /scripts /activate.bat from the root, as demo app is the name of my virtual environment. Note that I am running in the context of my virtual environment now, so let's jump to requirements.txt. I plan to access a SQL Server database in this video. So to do that, I will add PyODBC to the list of requirements. In addition, I will also want to visualize my data some, so let's add in references to two more packages, matplotlib and plotly.express. I'm going to focus on Plotly visuals in this series because I like how interactive they are, but I also think it's a good idea to keep matplotlib in reserve, just in case I'll need it later. Now that we have the requirements in place, let's run pip and install our requirements. This is probably going to take a minute or so to complete, so I'll let the console do its thing. In the meantime, I have a fair amount of stuff that I need to do. The first thing I'd like to do is create a file called config.json. This will be a simple configuration file into which I'll put my SQL Server connection string. We're going to connect to a local SQL Server instance using the ODBC driver 17 for SQL Server. Our database of choice is Chicago parking tickets, and I'll use Windows authentication to connect to this instance. Do I absolutely need to create a configuration file for this? No, not really, but it is a habit, so work with me here. Let's now pop into index.py. In here, I am going to add a few more import statements at the top of the page. We'll bring in PyODBC, Plotly Express, and the JSON library. The first one of these I'll use is the JSON library, as I need to read that configuration file. This is pretty simple. I'm loading a JSON object from disk and then setting the connection string variable to whatever value is in the config file. Next up, let's create some functions to query data in SQL Server. The first one I'd like to build is a function that will give some information about parking tickets aggregated on a monthly basis. There is a bit going on here, so let me explain it. The function's name is getTicketsByMonth. It takes in no parameters, and the first thing that it does is connect to a SQL Server using the connection string. Then I've pasted in a tsql statement. This statement uses a function called dateTrunc. dateTrunc has been available in some relational databases for quite a while, but just made its debut in SQL Server 2022 on the Microsoft's platform. It is also available in Azure SQL Database. If you're using an older version of SQL Server, you can replace this dateTrunc call with some other mechanism to get data by month, such as combining dateAdd and dateDiff, or you could use datePart to extract the year and then to extract the month, and put those two components back together again. Getting past dateTrunc, I have three additional non-aggregated columns: violation code, ticket status, and notice level. If you remember the filters from the prior video, these correspond to each one of those filters, and this is how we're going to be able to filter our data. After that, I have several additive facts: the number of tickets, as well as the total fine amount, total late fee, total collection fee, total amount paid, and total amount due. This data set contains information on parking tickets for the city of Chicago between the years 1998 and roughly 2018. There are a lot of parking tickets in this data set, so we'll focus on some fairly simple monthly summaries of the data. You are, of course, welcome to dive into the data and create some other neat queries to display on screen. The final line runs the read SQL function in pandas, returning the results of our T-SQL query as a pandas data frame. Streamlit has built-in capabilities around handling pandas data frames. And now I'm going to go back to the top line where we have a Streamlit cache decorator. Decorators in Python start with an @ sign. This one reads st.cache_data. What it means is we are going to cache the results of this function per set of input parameters. In this case, I don't have any input parameters, so we'll have one cached version of the data. If I added in input parameters for violation code, ticket status, and notice level, we would cache the results for each combination of inputs our users pass in. By caching this data in local memory, we don't need to go back to the database a second time if someone calls get tickets by month with the same set of input parameters, and that can be a considerable performance improvement. For our application, it saves having to look up the data in the database. In addition, that frees up database resources for other applications, as we don't need to keep querying SQL Server to get the same data over and over. It's typically a good idea to cache static data that you trust. We can also set the cache time to live pretty easily. This sets our time to live to 3600 seconds, or 1 hour. The idea here is that our data may change slowly, but it's okay if users are seeing data up to 1 hour old. But after an hour, we need to go back to the database again and get fresh data for this function and set of input parameters. The Streamlit team has put a lot of thought into caching, and I'll include a link to the documentation so that you can learn more about it. That's our first function. Now I'm going to paste in 3 more functions. These 3 all follow a similar pattern. We connect to SQL Server and run a SQL query to retrieve lookup data from some table. We return the results as a pandas data frame and exit the function. There's not a lot more to say about them, so let's move on and actually use the functions. Scrolling down into the Sidebar widgets section, I have to-do comments for each of the 3 filters I intend to include. Let's fill those in, starting with violation code. The first thing we do is get the list of violation codes by calling the getViolationCodes function. The first time we call it, we'll cache the data on our server. After that, calls will be pretty fast, as we just need to retrieve the data from memory rather than hit the database. Next, I'm going to display the violation codes as a select box. The select box is one of about a dozen Streamlit form controls for interacting with data. We have 4 properties that I've filled in. The label is a bit of text that will show up outside of the select box. I don't have an index, so we don't have a default selection for violation code, meaning that the user will need to make a selection if that user wants to filter the data. The third parameter is options, which is the list of viable choices. I'm getting the unique set of violation codes from my pandas data frame. Finally, I implement format func, which is a function defining how users will see the select box items. For each violation code, we will show the violation code itself, followed by the violation code's description. The code I'm showing is a little bit of a roundabout method for getting to the description, but it does work. Let's do the same thing for ticket status next. We start off the same way as violation codes, retrieving the ticket status codes. Then I create another select box with a similar label and no index. The set of options is our unique set of ticket status codes. Note that I don't need a format function because the ticket status itself actually is descriptive enough for us. Finally, we'll implement the notice level. This time around, I will put in not only the notice level, but also its description. And now it's time to run our app again. I'll need to make sure that I'm in the source directory as I kick this off because index.py is expecting a config.json file in the local directory. In the app, we now see 3 drop-down lists on the left-hand side, each of which includes a label. We haven't selected any violation code, ticket status, or notice level yet, so each one of those drop-down lists reads, choose an option. If I select the drop-down for violation code, we can see the violation code, followed by a hyphen, followed by the description. Notice that the drop-down menu does not exceed the width of the sidebar, so some of our text entries are getting cut off. There are two ways I can get around this. First, if I mouse over one of the text entries, we get a label on hover that shows the full text. That may be good enough for us, but the other alternative is to grab the sidebar and move it out some. I can drag this sidebar as far as I need it, and now the drop-down lists show more data by default. If I look at the ticket status dropdown, we can see that these statuses are pretty straightforward. The person has paid the ticket, the person received notice about the ticket, the person is scheduled to go to a hearing regarding this ticket, and so on. For the notice level dropdown, we have a few specific notice levels. So great, we have some filters. Let's next display our tickets by month on the page. To do that, I'll need to go back to Visual Studio Code, and then after that, we'll drop in a new block of code. The first thing we see is a header. This will show up under our explanatory block on the main screen. After that, we get tickets by month and save it as a variable. Then we check to see if any filters are set. Streamlit simplifies all of the JavaScript function calls like onClick and onBlur that we would normally have to deal with. As data scientists, we don't really need to think about that event model. Instead, we'll have a simple if block. If someone changes the value of violation code, then we enter this block that filters tickets by month. One important thing to remember with Streamlit is that every page action like this causes a postback. If I change the selected value in the violation code dropdown list, we're going to rerun the entire page. This means that we want to minimize the number of really expensive calls and cache most of what we cannot minimize. This behavior is quite a bit different from what we would expect with custom development frameworks, where we have a lot more control over when postbacks occur and we have asynchronous calls that can fill in results in the background. The next thing I want to do is aggregate my filtered data. I'll group by issued month and then sum up the rest of the columns. This works because all of my measures here are additive, so that makes it easy to group my data and see one row in the data frame per month, rather than one per month, per violation code, per ticket status, per notice level, which is the grain of our SQL query. What this ultimately lets us do is filter by violation code, ticket status, and notice level without needing to show those in the final graph. Speaking of graphs, let's add that in next. This adds a new header, number of tickets per month. We then create a Plotly Express line graph that shows the number of tickets issued per month. I also add in several hover data columns so that when I mouse over a given point in the graph, I'll also see the total fine amount, the total late fee, and more. Finally, we display the Plotly chart on our Streamlit dashboard using the Plotly chart function in the Streamlit library. I've saved index.py, so now let's switch back to the web application. I can see the button to rerun the app, so I'll do that. The first time you run this, you may see it take a while to bring in all of the ticket data from SQL Server. On my machine, this can take about 10 seconds to complete, but only the first time. After that, we've cached the result set, so any subsequent refresh of the page will be significantly faster, as I won't need to hit SQL Server again, and we can just pull the data right out of memory. Scrolling down on the screen, I can see a line graph with the number of tickets per month, just as I wanted. Let's mouse over these values. We can see each of our measures, though it can be a little tough to read them because of the way they're formatted. We don't have a thousand separator, nor do we have currency marks to indicate that this is in US dollars. But one thing I can do is slice this data. Let's change the ticket status to dismissed. That will refresh the page, and now our graph peaks at about 25,000 per month instead of 300,000. This tells us that somewhere around 5 to 10% of tickets get dismissed on a monthly basis. Just to show that we can cross-filter, let's pick a violation code. No parking in loop. Now it looks like there haven't been many dismissals since around June of 2009 when it peaked with 210 tickets going away for that reason. If I remove the dismissed filter, we can see that no parking in loop has basically gone away as a violation type. Now let's go back to the code because there's one more thing I want to do. This setup is fine, but let's say that we want to display a bit more information and not just the one visual. But maybe I don't want to pack it all on the page at the same time. we can use tabs to split out data for display. One important thing I need to note is that with tabs in Streamlit, we process all of the tabs, not just the currently visible one. That means that tabs are a good visual separator, but not a good logical separator. Nonetheless, this will work well for our circumstances. Creating tabs is easy. I'll add the following line of code after aggregating the data, but before plotting it. This will give us 3 tabs, and we can see the labels for each tab in the list. We'll want to convert our tickets by month graph into the first tab. To do so, I can simply use the phrase with tab 1 and indent everything. Then let's create tab 2 in a similar way. Tab 2 will show a bar chart containing the fine amount, the total late fee, and the total collection fee per month as components of the bar. This will give us an idea of total fees and how the sizes change over time. And I'll add in tab 3 while I'm at it. Tab 3 will display a table with monthly ticket data. I'm going to format each of the columns to make it easier to read on screen, and then I'll use the st.dataframe function to display a pandas data frame on the page. Let's save index.py and go back to the website. Then we'll hit rerun and see what changes. Immediately, we can see 3 tabs, and also that we're on the first tab of tickets per month. If I switch over to fine breakdown, I can see a bar chart with rather tiny bars. I'm going to remove the violation code filter so that we can see all of the tickets for a given month. Then, let's drill into a sample of the data sometime around 2015. I can use my cursor and drag into an area of the chart. Now we have a set of results that will be easier for us to see. In this time frame, we can see that the total fine amount is the majority of our cost, but that late fees make up somewhere around 20% of the total, and collection fees add a few percentage points as well. Our final tab is raw data, and that shows us a table. Because I've formatted each of the columns, it's fairly easy to see counts, amounts, and so on. Let's select just the results where the notice level is seizure, meaning that the vehicle is on the city's boot list. We can see 5 tickets in March of 2018. Those 5 tickets had a total fine amount of $475, but just as much as in late fees, and also $88 in collection fees. People have paid a total of $150 toward those 5 tickets, meaning that the city is still owed $888. That's going to do it for this video. In not even 150 lines of code, we have built a web application that enables filtering and interacting with the data across 3 different visuals. That's a lot of value for a dashboard that might take a person an hour or so to put together from scratch. And I think this is exactly the wheelhouse for Streamlit. Quick and dirty dashboards that data specialists can put together without having to think about event handling, post-back, result set caching, or other things that front-end developers typically need to care about. The next video will have us dig a bit deeper into the options around slicing, filtering, and visualizing data. We'll have links and show notes in the description below, and until we see each other in the next video, take care.